SIwave is a power integrity and signal integrity tool. DCIR, one of the power integrity solvers, is discussed in this video. DCIR is used only when all the dies that you have in your PCB, or the ones that you want to analyze, all of them are carrying a fixed amount of current, constant current, like TIAs, power amplifiers, drivers, and many other kinds of dies. If one of the dies is carrying a variable current, then you need to do DC plus PI. We talked about the PI in another video. DCIR is necessary to study the voltage and current distribution of the power plane distribution network, PDN. The solver calculates the voltage drop in any power plane, voltage rise in the ground plane, the current distribution, the current in each via, detects overloading in any via, detects any massive current accumulations, identify location of potential ESD issues, and many other defects. SIwave should not be used to build PCBs. While this is possible, it's not the best way to utilize SIwave. SIwave, when it imports any file, it extracts so many kinds of information. For example, the stack up, the material, the components, and the nets. So what is missing to do in SIwave is assigning ports. That's all. Then you are ready to start solving. Before using SIwave, it is highly recommended that the user reads the electrical schematic very well. It will save you lots of time. SIwave, like any other PI tool, understands the language of nets. When a board is imported, SIwave immediately starts looking for single nets. Let me show you some sort of a nice drawing here, showing you the definition of single nets. Any single net is an electrically connected structure without the use of any external component. A single net could occupy many layers but cannot be electrically disconnected. To analyze a power plane, one needs to identify its nets. It could have just one net, and it could have many nets. And if there are many nets, they should be connected using resistors or inductors. And that will construct what we call a passive link. If integrated discrete components exist along the path, then SIwave will treat each side of the integrated component as an independent link. So this is an independent link, this is an independent link. Treat them as two different structures. So you can see here, you can solve one net, you can solve one passive link, you can solve many passive link in a power plane, you can solve many power planes at once, but you cannot solve one power plane with an integrated circuit in between. This is not a valid setup. Great. So any process in SIwave, DC, PI, signal integrity, or radiation, starts by selecting a solver. Once a solver has been selected, SIwave generates, so if I click here, for example, and I click DC, generate a dialog box for you. Think about this dialog box as a form, where SIwave will fill up this form with all the information that it was able to extract from the file. For example, for the DC, when you click the DC solver, you will get this dialog box, and you see to the left in this section the list of all the power planes. And notice that SIwave always put the power planes in red versus RF lines and control lines and any other kind of lines are in black. That's how SIwave distinguish between them. That's how SIwave is telling you that it's recognizing these ones as power planes, while it doesn't recognize these ones as power planes. Of course, there is a way to shift between them. There's a way to change a power plane into an RF line, and an RF line to a power plane. But that's not the subject of this video. So If I select one passive link, let's say the 1.2 volt, so this link has only one net in it. This passive link has only one net in it. So what I need to do is to specify the location of the source and the probe, which is practically specifying the location of the ports. In any power plane, usually what we know is the voltage at one point, which is here at the output of the VRM voltage regulator. So usually we specify, we go here and we click and we select a voltage source. And we set it to 1.2, for example, because this is 1.2 volt line. Then what we also know is how much current is withdrawn by the loads. So in our case, we have a CPU, and we go here and we select to be a current source instead of voltage source or voltage probe. And we select 1 amp, just an example. So what does a current source? It doesn't mean that we have a current source there. All what it says that we only know that there is 1 amp current is going to enter that port, whether coming in or out. So that's the only information we know about our power plane. The voltage, we're sure of it, and the current at the load. And that's it. We are ready to solve. Of course, if you are analyzing many power planes, you can select them one by one. That's what's recommended. Select one passive link at a time and assign ports, voltage source and current source. Here you can, as you noticed, we have a third option or fourth option, which is a voltage probe. Voltage probe, practically, we're putting a probe where we want to know the voltage at that location after solving the problem. Terminal means instead of having a component there, we're going to replace it with a termination, a 50 ohm termination or any kind of termination. In my case here, I don't need to do that. I just need to know the behavior of the power plane, the link from the VRM to the CPU. If you have so many nets and you spend some time doing the setup, it's highly recommended that you save the setup. SIwave allows you to save the setup. Then later on, if you upload the same structure again, after certain modification, you can load the setup again and it will be populated for you. So you don't have to repeat the whole thing again. Now, if you have just one passive link, then there's no need to save because it's simple and straightforward. Great, so we're ready to start to solve. So we do configure simulation, which simply populates the ports and prepare the structure for solving. Once it's done, then we go validate. Validate practically looks at your nets, making sure that they are all as per recommendation. There's no violation of any kind. Everything seems to be okay, as you can see here. So press OK. Now we move to solving. So we click simulate. You put a name here. You can export the information for ice pack and mechanical. This is extra stuff here that you can do after doing the DC analysis. You can turn it on or off. Set uniform design temperature to this temperature. This is just affects the conductivity of the materials. In this table, anything that is a voltage source, make sure to put it negative. And all what the negative means here is that you are telling the system that the negative column here is the reference plane of this guy. But for the current source, it's highly recommended to keep it neither. Let the system calculate for you whether it's going in the positive or negative value. So that's the recommendation. There are other solver options practically, which is the accuracy. What kind of accuracy you want? You want optimum accuracy or you want optimum speed? You want to compute inductance and other stuff. If you want, you can select that, and you can save or export setting, and you can also import old settings. So I'm gonna keep everything the same, and we launch. So if you launch that, already exists, I will say yes, replace it. After finishing solving, you go to the results panel and you will find this. If you right click, now we come to the results. The first thing you're going to be looking at is a plot of the currents and the voltage. So if I click here, SIwave will produce this table for you. And in this table, you can select what do you want to see. So in my case, I want to see, for example, I will start by looking at the voltage on the VCC. So you click here and you look at the voltage on the VCC. I'm going to hide all the layers except this layer to look at the voltage. And as you can see, it gives you the voltage from the source, from the VRM to the CPU. And if you move the mouse around it, it will give you the voltage on each point in the model. And you can see this is the ground. See, the voltage at the ground is very small, E-4. What the user is looking for is a smooth transition of the voltage. One expects to see a very small changes in large power planes. But any significant delta means lots of power is being dissipated in the wrong way. Now, the second thing you would like to examine is the voltage of the power planes. Many designers make a mistake by simply focusing or examining the voltage in the main VCC line. You also need to worry about the voltage rise in the ground. So to do that, go to the top, make sure to go to the top where your components are. And in this table, activate the right layer to look at it. Then you can examine your ground. So you look for power planes ground. In our case here, let's turn off the voltage and focus on the ground. You can zoom in on the grounds. You can zoom in on the grounds and you can check what is the voltage seen by the die. So in our case, we are looking at 0.6 millivolt. That's a good sign. It means we are not losing too much on the ground side. If you see large numbers, then it means that the current flow in the ground planes is not correct. So it's not just focusing on the current flow or the voltage drop on the main line, also in the return path has to be correct. The third most important information is the current distribution inside your power plane. So the way you do it, you go here, you activated the current distribution, the current plot, and you look at the region of the VCC. And as you can see, it provides you information about the amplitude of the current as well as the direction of the current, both of them on the same plot. So this plot provides you information about any bottleneck issue in the power plane network or in the ground plane. SIwave, as I said, provides you two pieces of information in the plots, the current magnitude and the direction. Any concentration of currents will show up in red, must be examined by the user. If it turns out that the section is narrow, then one needs to find a way to widen it. Also watch for any sharp corners like this. If one notices that the current flows in an irregular way around sharp corners, then there is a potential for an ESD issue. Always, even with DC applications, avoid having sharp corners. Always make them round corners. It doesn't cost anything to make them round. But keeping them sharp will have a potential for creating ESD issue on the long term, and you don't want to do that. Now, what's next? The most important thing from the analysis of the DC is the via density. How much current is flowing in the vias? So to do that, to be able to see that, you go to display element data, and SIwave will populate this dialog box for you. So if you go and you select vias, SIwave will display all the vias and how much current is running through them. It also highlights if any via is carrying too much current. The limit is specified in a file called dc_coefficient.txt. The default numbers determines if the via will pass or fail the test, the limit. So you see here, there's a pass and fail. The user can change these numbers, the limitation numbers, but the default numbers are standards. If any via carries too much current, the probability of a PCB failure becomes very high. Designers then need to increase the number of vias in that area if you see any failure. Now, since we have this, we can also look at the density in the metal. SIwave can identify sections with voltages greater than or less than certain values. You can do that. It can also find regions with current density above certain value. It can also find regions where power density is above certain values. So these things, you can use them to examine your board section by section and make sure that there is nothing, no weaknesses within your structure, within your design. You can also look at the voltage probes. Remember, I was talking about the voltage probes. If you used any voltage probe, you will be able to come here and see what is the voltage value at that location. And the last thing you can see from this table is the power distribution. So I can look at the power distribution. Again, you can see that it is almost identical to the current distribution. This information is important if the user wants to do a thermal analysis. In this case, the IcePack program inside SIwave, if you go here, there's IcePack. If you click on this button, IcePack will take the power distribution and convert it into temperature distribution. That's all what it does. The power distribution is also used to calculate what we call the MTTF, which is this one, which stands for median time to failure. The MTTF solver is also available within SIwave. So power distribution is necessary data for more advanced calculations and important calculations that a PCB designer needs to do. From these values from the calculations of the power density and the current and the voltage, you can also calculate the loop resistance. And the loop resistance is practically the total resistance of the main line and the return path. So both the VCC and the ground summed together. Or you can go into more detailed information, which is path resistance. So path resistance will tell you how much is the loss on the VCC alone and how much is the loss on the return path. It will distinguish between them. You can look at it from here, or you can look at it from the RL tape. Both of them will be available for you, so you can tell which one of them is the main contributor to the total resistance of your power plane. In addition to do all these calculations, SIwave allows you to export things. So it can export a power tree. So what is a power tree? It is a flowchart. Let me show you how it looks like. And this flowchart summarizes everything in one place in a graphical way. So you can see the voltages, the current, the flow, the direction of the flow of the current. It is very important for the user to produce this flowchart to confirm that all the connections of all the power planes inside the model are correct. The flowcharts is the best way to confirm that. It also summarizes, as I said, all the results in a graphical way, making it easy to understand the current flow inside the PCB. So it is very important to do that at one moment of time. Plus, it produces a nice image for you so you can use it in your port. And the last thing I wanted to talk about is exporting SPICE netlist. So this will create a netlist SPICE model, and SIwave supports many of them, as you can see in this list, whether it's HSPICE or Maxwell SPICE, PSPICE, Spectra, or Simplest. After finishing solving the problem, the first thing you would like to do, especially if this is the first time you solve this model, is to check for refinement statistics. So what will refinement statistics? It will tell you about the convergence in this column 4. You need to make sure that the convergence is happening in a smooth way. If you see any disturbance going up and down, that's a sign that somehow something is wrong with the physical structure. Usually it doesn't. With the DC, usually it goes in a very smooth way. Also, the number here is where the system stopped. You can improve that by selecting optimum accuracy instead of balanced. The second thing you would like to check is the profile. So the profile will give you information about the mesh used in each section and the time it took to solve the problem. Now, this is important at the beginning, first to understand how much mesh has been used. But second is to compare different models at different times to make sure that everything is being solved in the proper way. So if you did something and you're happy with the results, you compared it to measurement, then you went after that and you solved another one. Make sure that the number of triangles are exactly the same. Then you know that the results can be trusted. The other thing you can do is you can also look at the simulation properties. Whereas this is practically is going to take you back to your setup. And this is important if you are reviewing the results after many months or years and you are not sure how these results were produced. Then you can select this option to see the setup that created these results. So in conclusion, checking the solution, displaying data in many forms, and exporting data in many forms. These are the things that the user of SIwave can do from doing SIwave, of course, DCIR solution.